And this is part one. Kind of the same thing we did with absolute value equations. We solved absolute value equations, but in part one we were limiting ourselves to absolute values of linear, and then we did absolute value equations where we had absolute values of quadratic. Same thing here. We're going to be looking at reciprocals of linear functions and also at reciprocals of quadratic functions. In general, though, we're going to be looking at how to graph and describe the properties of the reciprocal of a linear function. What does this mean? Well, if I were to look at y equals some linear function, maybe that function is 6x plus 3, maybe it's negative 3/4 x minus 8, but it's a linear function. What that means is it will have a straight line for the graph. What we are looking at here today is what would the graph look like and what would the properties of the graph be if we took that exact linear function, whatever it is, and we graphed 1 over it instead. That's what we're looking at doing. So if the original function is negative 2x plus 5, we're going to understand how to go from y equals 2x, negative 2x plus 5, to y equals 1 over negative 2x plus 5. And it's not as simple as just graphing it on your graphing calculator. That's not the point. All right, we have to review some very fundamental ideas. And those of you that interchange the word inverse and reciprocal better stop doing it. Inverse is not what we're talking about here. And I know that in junior high sometimes teachers even will use the word inverse. What they mean is reciprocal. Okay, so the reciprocal of a number a is 1 over a. And what I'm telling you is some junior high teachers might say, oh, the inverse of a is 1 over a. That's wrong. Inverse means something different. For example, if I said, what is the reciprocal of 5? It's 1 over 5. And I want to point something out to you. The reciprocal of 5 is 1 over 5, but the reciprocal of 1 over 5 is 5. So if I said, what's the reciprocal of 1/5? You would say it's 5. And my point is, these numbers are reciprocals of each other. If you know one of them and I say, what's the reciprocal of the other, you just flip it over. If you have a number that's already a fraction, like negative 7/3, and I say, what is the reciprocal of it? Could we do this? Could we use the definition that I've just given you and say, I'm going to take 1 over negative 7/3? Yes, you could. And then you would say, this is a complex fraction, so I'm going to multiply the top and the bottom by 3 so that these cancel, and I'm left with 3 over negative 7. But you don't have to use that definition of 1 over to get the reciprocal here. You can just flip it. And I hope you understand that if I go back to this and I take 5 and I flip 5, it becomes 1 over 5. Because 5 is 5 over 1. So there's a very non-mathematical kind of loosey-goosey definition of a reciprocal. You flip it. Whatever the number is, you flip it. The reciprocal of y equals f of x is 1 over f of x. So it doesn't have to be a number. If I go back to what I was talking about earlier, and I said, you know what? Y here is actually negative 2x plus 5. What is the reciprocal function? That. So it doesn't have to be a number, it can be a function. And the reciprocal of a function is just written as 1 over the function. I'm using a different illustration here. If a function has the equation y equals 2x minus 3, then the equation of the reciprocal function is, and there is either a typo up here or in your notes as well. It should say y equals 1 over 2x minus 3. Does yours say y equals? It does. So I'll have to fix that up here in my handout, but you're telling me you have the y equals in there. Good, you should. What we're doing today is looking at the relationship between those two things. That is to say, if you know a linear function of y equals 6x plus 2, what does that tell us about this function? And we're going to be able to answer this without graphing this on a graphing calculator, without using a table of values or anything like that. You can look at the features of the linear function on the left and tell me what the reciprocal looks like. But there's a lot of warm-up that goes into this. So this is the question. How does a linear function and the reciprocal, how are they related? And I don't want you to get ahead of me and graph them on your graphing calculator, because your graphing calculator, quite frankly, does a horrible job at graphing these. Sometimes. So we're going to do some basic warm-up here with regards to reciprocals. And it's going to require a little bit of thought on your part. The reciprocal of a positive number is what? If you take any positive number in the world and you take the reciprocal of it, will you still get a positive number? Absolutely. So whenever we reciprocate positive things, we get positive things. Similarly, the reciprocal of a negative is going to be negative. If I take 1 over a negative number to get the reciprocal of the negative number, I'm going to get negative. What is the reciprocal of 1? That's right, it's 1. Right? 1 over 1 is still 1. What is the reciprocal of negative 1? Negative 1. 1 divided by negative 1 is still negative 1. These two things, I'm going to occasionally be referring to these two as invariant. What that means is that anytime you take the reciprocal of a number, it's not going to change if the number was either 1 or negative 1. What is the reciprocal of 0? It's undefined. You cannot divide by 0. It doesn't exist. I don't know, I'm pretty sure I've told you the story of Miss Sikorsky teaching me in grade 2 how to divide with eggs. You know, I've got a little carton, empty carton, and there's a big basket of eggs on the teacher's desk, and she says, Paul, show us why 12 divided by 2 is 6, and the answer is I go up there and I can put 2 eggs in, and 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 2 eggs in. I can do it 6 times before it's full. But if she said to my little soft brain, what is 12 divided by 0, and I just stood up there like an idiot putting no eggs in, I would be there forever. So there's no real good definition of that, although in calculus we would say it's infinity. Okay? Or negative infinity, depending on the nature of things, but that's okay. 6 and 7 are very important as the absolute value of a number gets larger. So I want to just stop for a second and explain what I mean by absolute value here. You know what absolute value means, but my point is forget about negatives for this. Imagine there are no negatives in the universe. As a number gets larger, what happens to the reciprocal? So you can try taking the reciprocal of 2, and then taking the reciprocal of 3, and the reciprocal of 100. But what you will discover is as you take the reciprocal of a bigger and bigger number, you're left with a smaller and smaller result. One divided by, I'm going to go 5. It's a pretty small number. It's only a fifth, or 0.2. 1 divided by 50, it's even smaller. 1 divided by this number is 1.4 times 10 to the negative 8, which you should know means 0.0000000, and then 1,4. It's going to have 7 zeros and then the 1. It's very small. So as the absolute value of a number gets larger, the reciprocal gets smaller, but never 0. It gets smaller, and this is a hard thing to wrap your head around. You know what it's like? It's like those convergent geometric series. It keeps getting smaller and smaller. All the time it's going to get smaller, but it never reaches 0. It can't. The only way you can get 0 out of a fraction is if you have 0 on the top of the fraction, but a reciprocal is 1 on the top. As the absolute value of a number gets smaller, what happens to the reciprocal? So if I were to do this backwards and say I'm going to take the reciprocal of 0.4, it's 2.5. If I take the reciprocal not of 0.4 but of 0.006, it's 167 almost. You know, what's the reciprocal of that? Well, it's getting bigger and bigger. So as the number gets larger, the reciprocal gets smaller. As the number gets smaller, the reciprocal gets larger. But, I don't even know that there's a but here. It can just get larger and larger without any boundary or limit. It'll never reach infinity is what I was thinking. It can't reach infinity. But no matter how big it is, it can get bigger. All right. So we are going to consider the function y equals x. And I'm using function notation above. But here is, this thing that I'm going to highlight is the linear function. This thing that I'm highlighting in yellow is the reciprocal of the linear function. And I really hate writing fractions this way, but I want to make it fit. So we're trying to find a relationship between the linear function and the reciprocal. So I'm choosing to do this with a table of values and filling in the first column that's empty as child's play. Because if y equals x and x is 1, y is 1. If x is 2, y is 2. If x is 5, y is 5. Let's leave the yellow column for later. This would be -5, -2, -1, and 0. So now let's do the reciprocals. We're doing reciprocals of points right now, not of the whole graph. So this would be 1, this would be 1/2, this would be 1/5, this would be -1/5, -1/2, -1, and then undefined. So it's going to require a bit of thought on your part, but nobody said life was always easy. This, I'll do it this way. Is the x comma y of a point on the blue function. This is an x comma y on the reciprocal of the blue function. You with me? They're the same point. So we'll come back to that idea in a second. Similarly, this is an x comma y on the yellow function, and this is an x comma y on the original function. So that point is the same as well. Would you agree that 2 comma 2 is a point on the original function? Yes? Okay. Would you agree that the corresponding point on the reciprocal is 2 comma a half? Are those 2 points the same? No. Every other point will change except for this one, whoops, except for this point and this point, which is why they're called invariant. Okay. So now what we're going to do is we're going to do some plotting. So let's plot y equals x first. That's really pretty simple. We have the following points to plot for y equals x. We've created 0, 0, 1, 1, 2, 2. I believe I went to 5, 5 in the table, didn't I? We went and included -1, -1, -2, -2, -5, -5. And I do think it's worthwhile to draw a straight line here. You're all smart. You can figure out what you can use for a straight edge. If you're really artistic, you might be able to draw a pretty decent straight line by hand. You can use the edge of your calculator. You can use another pen if you want. You can use your notebook, your textbook. Doesn't matter. So this is what y equals x looks like. And it has arrows on the end of both ends of this line. I'm not going to put them. You need to know that. So that is y equals x. Now, what about y equals the reciprocal of x? Which I want to point out to you, this other function is y equals 1 over x, but more importantly, it's 1 over this function. This is f of x. The one I'm about to draw in brown will be the reciprocal of f of x, which happens to be the reciprocal of x. So let's start with the invariant points. I'm going to draw them not as solid dots because I want you to understand that it's still a red dot underneath there. Or, if you like, you're going to have to communicate this to yourself however you see fit. I'll just make it kind of semi-transparent. That might be a little too transparent. Right? There's still a red dot under there. I think you get that. But when we look at 2, x equals 2 produced a y coordinate of 1/2, didn't it? And did we do 5 as well? Was 1/5. What's going to happen as we move further to the right to these points we keep plotting? Owen, do you know?
It'll approach 0.
They're going to approach 0, and I like that terminology. They will not reach 0, they will approach 0. So this graph is going to get closer and closer and closer to the x-axis. Okay, let's keep that in mind. Let's plot over here at -2. And when you look at your table of values when x was -2, the reciprocal of that was -1/2. And when we go over to 5, the reciprocal of -5 is -1/5. So what's going to happen to these points when we go from -2 to -5 and we keep going to the left? What's going to happen to them is they will also be approaching 0. They will be getting closer and closer to a value of y equals 0. But because this curve on the right, which is above the x-axis, never reaches the x-axis, and the curve on the left, which is below, never reaches the x-axis, there is something which we call an asymptote. Now this dotted line, which is called an asymptote, it's called a horizontal asymptote. It's a weird word. Is not part of the graph, it's just telling you that the graph is going to get closer and closer to that line near the ends of that line. Where are the ends of that line? Infinity and negative infinity. It goes on forever. All right. We still haven't finished this. What about some other points? Now, I've plotted all of the points I had, but would you agree? I could use 0 and 1/2 for x. Whoops, not 0. I could use 1/2 for the x coordinate. And the y coordinate on x would be 1/2. Let's just look at that. That would be this point, wouldn't it? But what would the y coordinate be on the second function? Well, it would be 2. And what I'm getting at is instead of getting bigger values of x and y gets smaller and smaller, what if we get smaller values of x, then y would get bigger and bigger? So what's going to happen is we're going to get a point here. And if I were to go to, and I'm going to write this down because things are starting to pile up here. If I were to go to 1/3, let's go 1/5, then the original function would pass through 1/5 comma 1/5. Okay, but the reciprocal of 1/5 is 5. Which means as we get closer to the y-axis, and I look over here at 1/5, it's going to be up at 5. And the exact same thing is going to happen vertically as happened horizontally. No matter how close we get to x equals 0, we will get bigger and bigger and bigger and bigger and bigger values of y. But we can't reach x equals 0. Why can't we reach x equals 0? Because it's not allowed. It's undefined. When x is 0, you end up going 1 divided by 0, which is not allowed. So we also have a vertical asymptote. And we can put in some points on the other side. When x is negative 1/2, the reciprocal is negative 2. When x is negative 1/5, the reciprocal is negative 5. And we have to draw this. Now, I would recommend when you draw this, limiting your drawing to this. I wouldn't attempt to draw out to the 5s. And we simply are going to put a little arrow on the end of each part. And since it's right there next to an asymptote, we need to know that what that means is it gets closer to the asymptote. It encroaches on the asymptote. And the same thing over here. And that's what the graph looks like. Now, we're not done. It says, describe how the graphs of the functions are related. And there's a lot of ways you can answer this, but I want to highlight the important points. 1, wherever there's an x-intercept on the original graph, you will have a vertical asymptote. Now, just stop and think about this for a second. This is the x-intercept on the original graph, and it has a y-coordinate of 0, and if you try to take the reciprocal of 0, you can't. And I'm kind of going to go a bit in circles here. I might as well tell this to you now. If you want to go from y equals f of x to the reciprocal, this is what happens. you end up taking the reciprocal of all of the y coordinates. Look at this picture. What is the y coordinate here? 2. What is the reciprocal of 2? 1/2. What is the y coordinate here? 5. What is the reciprocal of 5? 1/5. What is the y coordinate here? 1/2. What is the reciprocal of 1/2? 2. So, because the y coordinate here is 0, what's the reciprocal of 0? Not allowed. So you get an asymptote there. So one of the things you need to make a note of is an x-intercept on f of x creates a vertical asymptote on the reciprocal function. There's a connection. It doesn't matter how many x-intercepts there are. I can tell you right now, and please don't write this down, I'm just trying to get you to think, that if I had this graph and I asked you to sketch the reciprocal function, there would be a vertical asymptote here, here, and here. Because the y coordinates at those points are 0 and you cannot reciprocate 0. What's another relationship? Well, another relationship, and this may seem weird that I'm pointing this out, is that as the red graph goes up, the reciprocal goes down. When you go left to right here, the red graph is always rising left to right. We said that as a number gets bigger, the reciprocal gets smaller. Well, what that means is as the red graph goes up, the brown graph has to go down, down. So wherever an original function is increasing, the reciprocal is decreasing. If f of x increases, 1 over f of x decreases. And the opposite would be true. If the function is decreasing, then the reciprocal will be increasing. And there's only one other thing I want to point out to you. If y equals 1 or y equals -1, what happens? What's unique about where y equals 1 or -1 on these graphs? Joseph, do you know?
The reciprocal is just 1 or -1.
Right, so it's invariant. These are invariant points. Now, for the remainder of the lesson, we're not going to do the graphs by making tables of values. We're simply going to use what we learned from the first warm-up to answer the remaining questions. However, any questions at all with the first warm-up? All right? So, consider the function f of x equals 2x minus 4. Would it be a safe bet for me to say to you that I expect you to know what 2x minus 4 looks like as a graph? It's a grade 9 thing, actually. You should know by looking at that the slope of that line is 2 and the y-intercept is -4. What is the reciprocal function? I'm not trying to trick you here. If the function is 2x minus 4, the reciprocal function is 1 over 2x minus 4. It's that simple. What is the equation of the vertical asymptote? Okay. Well, the vertical asymptote will occur wherever there's an x-intercept on the original function. An x-intercept on the original function is found by changing y to 0. That's pretty easy to solve. You add 4 to both sides and divide by 2, and you get an x-intercept equal to 2. Are you with me? And that means x equals 2 is a vertical asymptote. And we'll draw that in a bit. There's another way to look at it. Do you agree you're not allowed to divide by 0? But that means if you're not allowed to divide by 0, then that's not allowed to be 0, is it? 2x minus 4 can't be 0. Well, if I take 2x minus 4 and say, you know what? 2x minus 4 is not allowed to be 0, I solve that and get x is not allowed to be 2. Well, that explains why there's an asymptote at x equals 2, because x is not allowed to be 2. Sketch the function and the reciprocal. So it was y equals 2x minus 4, right? Y-intercept of negative 4. I'll write this here so we can see it. Y-intercept of negative 4, slope of 2. So over 1 and up 2, over 1 and up 2, over 1 and up 2, etc. This is what the graph 2x minus 4 equals y looks like. And again, do your best to draw a fairly level line there. Yeah?
Our graph is small.
Your what?
Our graph is smaller.
Your actual grid?
Yes.
What does it go to left and right?
3.
Really?
3 maybe.
Okay. So, well, that's got to be fixed. So, that's not what I wanted to do. So, here is your grid, correct? So I would give you a proper grid if I asked you to do this on paper. But you can see that the x-intercept is 2, which we've already established, by the way. And the slope is 2, so it goes over 1 and up 2. Man, that ticks me off that I've got the wrong grid there. That's okay. So would you agree that that's what 2x minus 4 looks like? Is there any place on this graph where y is 1? Y is equal to 1 right here, isn't it? So that will be invariant. Is there any place where y is negative 1? Yes. So these 2 points will be points on the reciprocal. We also know you are going to have a vertical asymptote here. And what I haven't told you yet, but I'm about to now, is in this course, and it changes in 30, the x-axis will always be a horizontal asymptote. So what does this reciprocal function look like? Watch what I draw. It doesn't need to be perfect. Watch what I draw. Whoops. Done. As the function goes up, the reciprocal goes down. And those little arcs that we draw, do you see they are always in the corner of 2 asymptotes? They have to be. That's it. That's all you need to know how to do. Now, let's write the equations of these asymptotes. This equation is x equals 2. What is the equation of the horizontal asymptote? Ryan, do you know?
Y equals 0.
Y equals 0. Perfect. Any questions with that example or warm-up? So summary, what do you do when you sketch these graphs? And this is in your notes. You sketch the vertical asymptotes, and they are wherever you have an x-intercept of the original function. You identify the horizontal asymptote as always being the x-axis in this class. You identify invariant points, and then you draw your curves. That's it. Be a little bit more complicated tomorrow. So let's take a look at this one. The graph of a reciprocal of a linear function is shown. There it is. We have to work backwards now. You don't have to like it, but we have to work backwards. If this is the reciprocal function, this is y equals 1 over f of x. What is f of x? What is the linear function? Well, there's a number of ways to go about it, but if 3, 1/4 is a point on here, then it must have been 3, 4 before, because we reciprocate y to get the new y coordinate. So we have a point here that it passes through, 3, 4. Can somebody tell me if there's another point that we know this straight line before we reciprocate it? Another point that this straight line passes through.
X equals 2.
And what's y?
0.
Right. It has to pass through here. Why? Because wherever there's an x-intercept on the original function, there is a vertical asymptote. So it passes through 2, 0. And this question has turned into a Math 10 question. Basically, we know that it's a straight line, so it has to fit this. So we need to know the slope. Well, how can we find the slope? Well, you know 2 points. Rise over run will give you the slope. I can see the rise is 4. And what's the run? 1. Goes over 1 and up 4. I don't even need a slope formula to determine that. From here, it goes 1 to the right, and then it goes up 1, 2, 3, 4. So that makes the slope 4 over 1. And I'm going to, for the final part of this, I'm going to write y equals 4x plus b. And I know that we're not all where we need to be in Math 30 when we start, but we're getting there. And I'm trying to train you or condition you to think certain ways. What do you think I'm going to call b? B is the y-intercept, but I'm going to call it something. And I've used this language before. Let me ask you a question. Is b a variable? No, it's not a variable. Variables are x and y. What is b called? It's a missing parameter. And how do you find it? You put in an ordered pair. We can put in any point we know. Let's put in x equals 3 and y equals 4. So I'm going to get 4 equals 4 times 3 plus b. That's pretty easy to solve for b. It's -8, I believe. You have 4 plus 12 equals, or 4 equals 12 plus b. So b is -8 when we subtract 12. The equation then is y equals 4x minus 8. How many of you already figured out that the y-intercept was -8 by following this backwards in the opposite direction? Could do that. Down 4 over 1, down 4 over 1, you hit the y-axis. This is just part 1. So the reason why these questions say A and B is because C and D, for example, are quadratic. We don't know how to do those yet.